Hello, everybody. Welcome back to one of our seminar RAS. Today, we will have Mickaël Dardaillon, who is a professor at Insa of Rennes in France, who will make us present for us his work. Go for it, Mickaël.
Okay, thanks Hervé for the introduction. So today I'm going to talk about Dataflow code generation for Fpga. This work was done with Alexandre Honorat and Jean-François Nezan, both at Insa Rennes. And this is still a work in progress, so we hope to have more results before publication. But I'm going to start first giving a few ideas about the Fpga and how we see them for this work and what are the challenges that we face. So context, what is interesting is that even though I'm coming from more the embedded side, we have a similar constraint to nowadays in HPC, is that we are looking either for high throughput or low latency. And we are looking for low energy, which is quite new for HPC, but has been a long time focus in embedded system. And there are multiple kind of processor, kind of computing system, going back to some of them just to give you a refresher and compare to what I expect to be an Fpga as a very high level. So first we got our classic CPU, which has an external memory and then a big lump of cache memory to be able to, for the ALU and the control to access quickly the memory, and there's a good bandwidth between the two to be able to accelerate run. And that is the classic do-it-all processors that we all have in our desktop. But we got also some specialized hardware, GPU being one of them, with same external memory, but a lot of very small arithmetic logic units programming more SCMD or SCMT manner. We still find some small memory and control to control the row. And the idea is to increase the density of the ALU and also increase the bandwidth to be able to process a lot of data. And there is also the Fpga, which has gained interest these days in HPC. The idea here is still have this external memory, cannot store everything on board. We got a lot of different computing resources being either computing or memory and completely distributed on the chip. And the configuration is going to connect those things together to create memory. And that also those resources are also heterogeneous in that we have memory and computation, and we got different scale of memory, like very small register and larger kind of scratch pad, which are integrated, and DSP and small ALU, which are all distributed on this Fpga. So this enables to create some specific circuit, which can be interesting. I'll talk into that in a second. What is the main difference with GPU is usually we get a much smaller bandwidth to the DRAM. So we're going to have a real bottleneck here to be able, if you want to exploit all the resources which are on our Fpga. That's a very, very high level point of view of the Fpga compared to other architecture. And one thing that we in our team find interesting is Dataflow programming. I think it's a natural expression for signal and image processing. Can be also for other applications. This is the kind of application that we usually address. The idea is to be able to connect a certain number of actors, which are kernels together, which are going to communicate data between them explicitly and do a form of computation. So it exposes a lot of parallelism, etc. Yeah, some kind of parallelism. I'll go back to that. But if we want to map that on an Fpga, what we could do is that we could put the different kernels which are here directly map on the resources of Fpga to do the computation. And then first idea would be to connect the FPGA to an external memory, so it does its computation and then send back the result. And the second computation can, so we got high throughput in that sense that we got these resources always available, and it's going to compute for the first image, second image, etc. And then if we want to do the computation for the second actor, we could do the same by reading the data back here, computing, and then writing the data. And we wait for the first image to be completely available, and then we get small synchronization here, which could start this second processing in our pipeline, etc., etc. The challenge by doing this computation here by always accessing the external memory is that we're going to have a high bandwidth usage and a high memory usage. This is going to also to create a long latency because we get to wait for a whole computation to be over before we can start with the next step of our computation. And this can be quite expensive, and it's not the right way to use an FPGA. Another way to use an FPGA, if we restart from scratch, put the same kernel here, is that we're going to do this computation for the first kernel, so it doesn't change, but we're going to store the intermediate result directly inside the FPGA, in the scratch pad which are available. And then we're going to start the second computation as soon as the data is available, the first tokens are available. And this is going to reduce significantly the memory usage, which will make it able to fit the data inside the FPGA. And we got synchronization mechanisms that we can build directly inside the FPGA to this small scale synchronization. And this is going to reduce the bandwidth usage here for our memory. And this is also going to reduce the latency. If we look at one image, which is processed by Gaussian blur 1, Gaussian blur 2, and difference, it's going to be much faster here to reach the result because we're overlapping the different computation. So we got a lot of gain to have from that. And we think that Dataflow is a very good way to express this computation on the FPGA. Then how do we do that? So we think that Dataflow is a natural expression for scenario image processing, and pipeline implementation, as we've seen coming from Dataflow, is a good match for FPGA. And we got native support in Vitis HLS. It's the tool from Xilinx, one of the big Xilinx AMD, one of the big supplier of FPGA. We can directly program that in C++ by declaring all the streams, so the FIFO between the actors, and declaring all the kernels with a few pragmas, and that works. That's not the easiest way to write a graph, but that is something we can do. We need to explicitly write all the FIFOs and connect them correctly, which is a first challenge, more syntactic, let's say, on the way you write, but that can be done. And the depth is really a challenge. What amount of memory do we need there? That will depend on the hardware itself and how it's created, and that currently is left to the user, which I think is not the it's a real challenge, and it's very difficult for a user to do. So in terms of challenge that we see and that we want to address in this work, in terms of design productivity, we want to express Dataflow at a high level. We don't want to write all the FIFOs and all the actors. And we want an optimized hardware implementation. At the end of the day, we want something that runs fast. So the contribution that we propose here is a Dataflow code generation for FPGA using high-level synthesis, using the Prism tool, which is developed in our team, and automatic scheduling and buffer sizing, which is very important because that's one of the main challenges today for people, even if they are willing to write a Dataflow pipeline implementation FPGAs and need to do this buffer sizing. It's a real challenge. And we propose everything as an open source implementation in Prism. You got the address here. And you can ask Pedro here, who's also working, knows a lot about Dataflow and Prism, if you have any question later. So we got two big contributions. I'm going to present them one by one. First, the Dataflow code generation for FPGA using the high-level synthesis, and then automatic scheduling and buffer sizing. First things first, Dataflow code generation for FPGA using high-level synthesis. So we're starting from a PySDF graph based on Prism. So that's our tool where we can create a graph. We have a UI to directly create actors and connect actors together. This is completely parameterized, is that we can provide value of parameters. So for example, size of the columns and row if we want to process an image. So that's a template, would be equivalent to a template. This is interface if you want to have subgraph that will support that. And this is synchronous data flow. Synchronous data flow means that it's multi-rate. So an actor can produce 100 pixels, for example, and this one is going to duplicate them one by one, and the graph is going to compute automatically the repetition factor, how many times each actor needs to execute for the whole graph to compute for one iteration, so one image here. And two things which are very interesting with synchronous data flow is that we can prove that we have create a deadlock-free implementation based on the model directly. So this is quite important in terms of property. And we can do automatic scheduling and buffer sizing to provide this deadlock-free implementation. So this is what we did here, is that we take this graph, our running example. The user is going to provide the kernels. So for all of those computation, you need to write the kernels. So we are going to use high-level synthesis. I don't know if everybody is familiar with high-level synthesis, but the idea is that FPGA can be programmed either in a low-level RTL language such as Verilog or VHDL, but they can also nowadays be programmed using C++ language, and the C++ language is transformed to this RTL level using a high-level synthesizer, such as Vitis HLS. And our kernels, so we write them directly in C code, and then we're going to provide the FIFO interface. So all actors are going to read into FIFOs, token per token. Those are called stream in the HLS world. And then in terms of code generation, so the user is going to construct the graph, but the code generation is going to generate the connection between all those actors, support everything that is multi-rate, that is something that is not supported natively by high-level synthesis. We support cyclic graph, and we prove that they are deadlock-free, which is quite a challenge. Something that is, again, definitely not supported by Vitis HLS. And we follow a self-schedule as soon as possible execution, which means that we are going to reach always the highest throughput given an amount of buffer. And the code generation is going also to generate all the input and output interface. Those are based on array, and we're going to do batch transform from and to RAM automatically for you to have an efficient implementation. And this is scheduled by host. So we are going to also generate a host code, which is not represented here. So this host code is going to enable the user to control the FPGA from a processor. If the FPGA is an accelerator board inside the large computers that could be running on your x86, for example, or in the experiments that we ran, we had an FPGA which included an ARM core, and we were running directly the source code inside the ARM core and controlling the FPGA this way. And we got different approach, an OpenCL, very HPC-like approach. We got the PINK, which is a Python proprietary interface from Xilinx, very easy to use. We got a bare metal implementation, which is directly C level to reach the highest performance and lowest overhead. And we generate all the test bed to be able to test that the graph is really working, and for the user to test their application even if they are not using the programming in FPGA. So that's one thing also, is that you can test application without running them on FPGA. And that is property that is coming from HLS and we are happily reusing here. There is a compilation flow that we created. So the user is going to write all the kernels, is going to use Prism to connect those kernels together to create a graph. And then our tool is going to take those two inputs, and based on Xilinx Vitis, is going to compute all the timings to know the performance of each actor, gather all those information inside Prism, compute all the buffer sizes, and then is going to take all the kernels and put that into Vitis to be able to generate a bit file, which is the file which is created to program Fpga, as well as a CPP code for the host, if you are programming using bare metal or OpenCL, or there is also a Python code for the pink version. So that's the idea of the compilation flow, more on the tooling side, and we got all of that automated, which enables us to do all our experiment and is the programming of FPGA. But one of the main challenges that is left is buffer size. Computing those buffer is really the scientific challenge that we are facing in this work. So I'm going to spend the rest of the presentation talking about that. And we're going to talk about the automatic scheduling and buffer size. First, with the program. We want to match the actor and the hardware execution model. So Dataflow, basically, when it was created, was mainly for processors. So we usually use in Dataflow an acquire release system with for shared memory synchronization, that an actor which is producing 4 tokens is going to wait until there is a space at least of 4 inside the FIFO, then is going to fire, means execute, and at the end of its execution is going to wait again to have the data available. Same here for the actor. If it's going to wait if it has enough tokens available in the input, then it's going to fire to consume those tokens. And then last cycle, going to wait again to have enough tokens available, etc., etc. Those two actors in this way are able to execute in parallel, but with a shared memory synchronization. What does that mean in terms of execution? Is that the actor is going to execute for a certain number of cycles, then we're going to have the actor B, and then if we have only 4 tokens, a space for 4 tokens inside this FIFO, we're going to wait until B has consumed all the tokens for A to execute again. So this model is performant on processor, but here on FPGA we are looking for much smaller grain in terms of synchronization, because here I've got only 4 tokens, but if my actor was producing wall image, I would have to store the wall image inside my FPGA before start computing the next running the next actor, which is going to cost a lot. So there is some work which has been done in SDF. So for example, there is SDF access pattern, where we are going to represent for each cycle, cycle by cycle, if an actor consume or produce a token. Here it's producing 4 tokens at cycle 2, 3, 4, and 5, for example, and this actor is executing in 2 cycles and consuming 1 token per cycle. This requires cycle accurate info. This is going to have scalability issues. If you think that you're going to run, analyze this, but have a full image, a full HD image, so more than 1 billion pixel, and you read 1 pixel per cycle, means that you're going to have to analyze a huge problem. But if we look into what this model is able to provide, is that actor A execute, and as soon as produce token, actor B is going to be able to consume the token and execute, which means that we have a much lower latency and a lower memory usage. So that's a way to use an FPGA, but those approach have some issue that we security info that you may not have, especially us that we are outside the HLS tool. We don't have the scheduling information from HLS, and scalability, which is a real problem in general. There's also more recent work using CSDF. That's another version of SDF, where we present The production and consumption as a series, which are repeated, and we can have something which is also we can repeat whole sequence. So that's a more compact way to represent the problem. We are facing the same challenge in terms of accurate information which are needed, and we still have the same scalability issue if we want to simulate that. So we're going to try another way to try to abstract more the system and use different tools to do that. So we're going to do an affine approximation. For example, we got an actor which is producing 4 tokens per execution, and it's executing for 8 cycles. So same actors that we've seen before. So the number of production is 0.5 token per cycle. 8 cycle, 4 token per execution, we divide the two. So we get a linear approximation of the number of tokens which are produced. The real production could be either produced later or produced sooner, but it's something that is around along this trend here. And what we're going to do is compute bounds based on that. So we're going to have a lambda for the upper part and lambda for the lower part. And then we can bound the production between the number of cycle times the production cycle. And those are those two bonds which are represented in green here and red here. And the production is going to happen during in this window. So that is some information that we can have and quite easily based on only those information. So I have to say we are going to try to find those based on those information. Here I represented knowing exactly the blue line. And now I'm going to do that with only those information. So that could be produced very early or very late or be in the middle. So we're going to compute our worst case bound based on the number of production and the interval of initialization. And those two bonds are going to be equal. So lambda that I call is the distance between my average production and this bound. And we are going to be able to bound our production in this way. And based on those constraints that we can compute for each FIFO of each actor, we're going to define an affine scheduling, a periodic scheduling based on several ILP constraints. I'm not going to go into details into all of them. This is some works that we are reusing, which was not applied to Fpga, but to other programs in SDF in general. And we're going to have an underflow, meaning that an actor cannot execute before it has token available. An overflow, which is going to take into account the size of the FIFO. An actor cannot produce token if there is not enough size in the FIFO. And we're going to take into account all these cycles to be able to balance production and consumption in the cycle. If one branch of the cycle is slower than the others, then we need to have enough space for all the actors to execute and store the token, not create a deadlock. This has been formally proven. This is Anand Bouaka's thesis. As I said, I'm not going to get into details, but they give us a FIFO size. If we have dailies, we can implement them. So initial tokens in the FIFO and a phase, which is going to present when the actor is consuming. This is pretty fast for an LP formation because we have only 3 variables per edge. That doesn't depend on the number of tokens which are produced per edge. So that's going to be quite easy to solve. And we are guaranteed to have the optimal throughput. So there is not going to have any pushback by overflow based on this system. So the idea is that we took this approach and we put it to the test by implementing it and comparing to some other approach. So I'm going to present the results that we have so far. This is the part where this is still a work in progress. We have only a few applications and some first results. But the setup is that we got our experiment based on Prism modeling. So we are using an SDF model with no resource sharing. That means that each actor has its own kernel, its own hardware, they're all running in parallel. Actor timings are extracted from Vitis high-level synthesis, which feeds the model for scheduling for maximal throughput. And the performance was verified using Vitis HLS co-simulation. The co-simulation is when you run your HLS inside VHDL mode as a cycle-accurate, cycle-by-cycle simulation. This is something that is quite slow, but enable us to verify the exact performance and the absence of deadlock to make sure that our implementation of the algorithm is correct. And in terms of buffer sizing, we have 3 different approaches we compare. First is the ASAP. So as soon as possible, we get a periodic as soon as possible scheduling based on SDF using the array approach, as I've shown in the beginning. So the acquire release approach, where we're going to produce all tokens at once and then consume all tokens at once, create a much larger FIFO, but this guarantee us that we reach highest performance here. And we're going to compare that with Vitis co-simulation. So Vitis is able during co-simulation to do profiling and propose some buffer sizes. So this is comparison to state of the art in terms of hardware, in terms of industrial tool. And we got ADFG, so the Affine Dataflow scheduling that I presented just before. I'm going to compare that on 3 applications, which are completely implemented and functional on Fpga. First is Gaussian difference. So that's our running example from all the slides that you've seen before. So we get those 3 approaches, ASAP, Vitis cosim, and ADFG. What I'm going to be interested in is BRAM, so the amount of memory that is used inside the FPGA by the FIFOs. So if you use an ASAP scheduling, we get more than 1,000 BRAM which are used, compared to Vitis cosim, which propose usage of 5 BRAM, and ADFG will propose a usage of 12 BRAM. So clearly Vitis cosim in terms of memory usage is best by far, by factor 2 compared to us. The challenge is that even for a simple application, for ASAP and ADFG, we don't have official measures that we run, but we can say that it's less than 10 seconds. I'm using a UI, so I'm not able to measure exactly, but this is very fast to run this or both those approach. Vitis co-simulation is taking 2 minutes, even for a simple application like that. And what we see is that ASAP is completely storing all the data in the intermediate FIFO, so this is very expensive. Vitis cosim is proposing to have for this FIFO here, which is going between the second and the 4th factor and bypassing the 3rd actor, so it needs to store token while it's their process here, proposing a FIFO of 730. That's most complicated to compute, and ADFG is over approximating by 2,500. So some over approximation here. The main challenge is for all the other FIFOs, which are just needs only a few tokens to be able to execute, because as soon as one is produced, the next one can consume. So the real size of the required FIFO is between 3 and 5, and we are also asking for 2,500. So here is the limitation of ADFG. This is an upper bound of the number of tokens which are needed, but is clearly not a required number of tokens, number of space. So then we got another application. So same idea is that we have multiple kernels which are computing data sequentially and then exchanging data. So it's at multiple filters which are doing a color filter, and we got data going all the way from the beginning to the end. And if you use the ASAP approach, we're using more than 2,600 BRAMs for a FIFO. Vitis is only proposing an implementation with 18, and ADFG is 60, so a factor of 3 here. Here we can see the runtime. We are reaching, I think, 1.5 hours to simulate this graph, which is not that difficult. Not 1.5 hours, but a large amount of time. And for the main FIFO size, we have a factor of 3, 4, once again, in terms of dimensioning. And for those FIFO, it's more of a mixed bag where we can find same the minimum buffer size needed, but sometimes we get a factor of 2 or 3 compared to FIFO size, which is found by Vitis. And the last application, the largest by far, is wavelet transformation. So that's a classic transformation in image processing where we have our data coming and then a bunch of filter coefficients. And then we're going to apply filters and downsampling, which reduce the number of sample, and then another filter, and then downsampling. So this is completely multi-rate. There are a lot of cycle, undirected cycle, where we are going to have FIFOs connected between the different actors, and which are going to store intermediate results here, which are going to be quite expensive. And then here we ASAP implementation is using huge amount of data once again, but it gives us a reference and make sure that all other applications reach the same level of performance. So that's good. Here's a runtime for Vtsco simulation to co-simulate this graph and determine the memory is 1.5 hours. This is 1.5 hours I was talking about before. And our approach is still less than 10 seconds. So here we see huge factor. And we got a factor of 2 in terms of memory usage with some very good results. For example, on those FIFO here, we are reaching nearly the same value. Other which are sending data much further, we have nearly a factor of 10. And then for those FIFO size, it's a mixed bag once again, where we're going to sometimes to use much more FIFOs than needed. And sometimes we have good results. So far on those different applications, what I can say is that we got an approach which is very fast, which provide a guarantee in terms of number of tokens, but this is a required, not sufficient tokens, and this is very large. So we are currently investigating to maybe run another algorithm on top of those results based on our first bound to try to get closer to this bound. This is still work in progress that cannot present yet. So in conclusion, we presented 3 contributions here. We got a Dataflow code generation for Fpga using high-level synthesis, where we are able to automatically generate the code for this, and code which was not easily supported in classic high-level synthesis tool. We got automatic scheduling and buffer sizing, which is very important, and which is the biggest challenge for developer to write, even if they are willing to write a graph in C code, then computing those buffer sizes can be a real challenge. And we got an open source implementation in Prism. So future work is that we want to improve buffer sizing. So if we could use other information, because right now we are using only the execution time and the number of tokens which are produced or consumed. If we could have additional information such as data dependency, knowing that a token cannot be produced before full 3 lines have been read, for example, could tighten our estimation. Or if we had directly access to our internal scheduling, we could build a more precise model, maybe at the cost of additional complexity, but there is maybe a trade-off to find here. And we're targeting right now we're targeting only as Fpga with the host code, which is just enabling us to run the code on the Fpga. But targeting a heterogeneous platform with Fpga plus CPU would be a real challenge, because we have to address mapping and scheduling and code generation in a heterogeneous way, where the scheduling that I presented, we've seen that it's very different when we are scheduling for Fpga compared to CPU, what is efficient. And mixing the two would be very interesting. And then we got design space exploration. So we could do constraint-based optimization to try to find the best implementation. Right now, we are only trying to reach the highest throughput, and there is a lot of memory optimization still to be done in terms of buffer sizing, but also in other terms, in terms of which kind of memory are we using? Are we using local memory? Are we using external memory, etc., etc.? So that's all for me. Thank you for your attention, and I'm now ready to answer all your questions.
Thank you, Mickaël. Very interesting presentation. Do we have any question? Yes, Lisa.
Hi, Mickaël. Thank you for your presentation. It's nice. First of all, one thing I want to know for your experiment purpose, which type of FPGA you are using right now?
Right now we are using Zinc FPGA. So that would be
Zinc Ultra Scale Plus? Zinc Ultra Scale Plus?
No, the Zinc
Z-board?
The Z-board, yes. But the approach by itself, I'm running the experiment on this FPGA because it's the one on my desk. But the approach is completely compatible with the Ultra Scale Plus. I haven't run, so I cannot say that it's running on it, but there should be no difference in terms of code. Maybe there is one or two things in terms of the interfacing with the host, but that should be all the same.
Okay. No, I asked this question because as I understand what you are doing, if I understand correctly, please correct me. In your research, you are trying to find out automatic scheduling thing for buffering, automatic scheduling and buffer sizing. This buffer sizing you are considering in the case of where you have some kernels inside FPGA, and each kernel is communicating with each other through AXI stream protocol. And when we are using AXI stream protocol, then we have to have some FIFO inside each kernel. So you are trying to find out a resource efficient way that how much FIFO you can allocate for inside FPGA. But that all definitely depends on how much resource the FPGA has, because Z-board is very small board, very small FPGA compared to Zinc UltraScale Plus. And also in Z-board, it only have BRAM, which is a small size, that's good. But also in FPGA, we have Ultra RAM. Zinc UltraScale Plus technology have Ultra RAM. You can use this Ultra RAM so you can make so that you can use more memory, more buffer size. And Ultra RAM is pretty technology wise. Ultra RAM is pretty much little bit faster than VRAM. So that's why I was asking that which FPGA you are considering. Okay. My next question is
if I just add one thing, that was a very good summary of my work. Thank you. And some of the things that to consider. Right now, I have to say that we are abstracting completely the platform by using Vitis HLS. I'm just giving FIFO size, and I leave Vitis HLS to map that to the best hardware. Which means that for very small FIFO, like we've found some FIFO which are 2 or 3 tokens, that will be mapped even to registers. Larger FIFO will be mapped to BRAM. And if we tried on the Ultra Scale Plus, I trust that Vitis HLS would directly map the larger FIFO on Ultra RAM. So in this way, that can be addressed. But right now, we are blind to the resources that we use. We haven't tried to optimize the kind of resources that we use. That is one thing that we are looking at right now, also to explore the size of the FIFO, because if we say a size of 5,000, but hey, maybe a BRAM can fit 8,000, so no need to optimize more.
Okay, right now you are you are doing. I mean, Vitis is doing this for you, right? I mean,
exactly.
You are not. Okay, I understand. Okay. Yeah. Thank you. This is all for me. Thank you. Thank you very much.
Thanks for your question.
Thank you, Lisa. So as you probably understood, Lisa is our FPGA expert.
That's very kind of you. Thank you.
Pedro, do you have a question?
Yeah. Hi, Mickaël.
Hi.
My question is, as I understand, this new scheduling and buffer sizing algorithm uses ILP, right? IR linear
Yes.
programming. Yes. And does it apply only for the FPGA target, or could this also be used in normal, like traditional Dataflow?
Software.
Yeah, in software, the Anand Bouaka's thesis was done completely, his work was done for software. So those were first applied in software for more real-time system. So using Dataflow for real-time system, but they definitely can be used in this way. We extended this work to FPGA, but they were originally done on software.
Okay, yeah, because I was very interested. I'm taking ILP right now in classes, and I think this is something that I could have used maybe.
Yeah, that could be something that we could look at.
Was it a big difference in terms of resources used, using this in comparison to what was there before?
Well, the idea is that before, as I was talking more in the beginning here on those slide, the acquire release, which is a memory that is usually used, and this kind of model also is used by the ILP formation for processor, is clearly wasteful on FPGA. Those are approach that I found so far directly addressed for SDF have real issue in terms of scalability, where if we try to address large systems, the access pattern, for example, they propose an optimal way to implement that using ILP, but there was one variable per cycle. So and per FIFO. So you reach something which is more several million variable. So your ILP param just explode. And that doesn't work. And CSDF is the same way. Other related work which are happening currently are looking into Affine from relation of scheduling, looking into the polyhedral model to be able to do some scheduling. I have a hard time to compare exactly what are the drawbacks and advantage of those approach, but they'll be closely related to what we do because they're also expressing in an affine way the scheduling information.
Interesting. Okay, that's something to look into then.
Yeah.
All right, thanks.
Welcome.
Thank you, Pedro. Any other question? No, I have some. I was wondering if there was any caveat of mapping new application, because I know as a fact that Prism have a lot of other application, and I was wondering why you didn't try them, execute them.
The challenge is maybe I didn't stress enough. The people who are aware of HLS may have already understood why I wasn't doing that. Is that even though we are using C code, those CPP kernel, HLS kernel, they need to be rewritten from scratch to reach any kind of performance on FPGA. Even though it's the same language, it's a completely different implementation. So there are some applications that we reused. As a matter of fact, the Wavelet is an application which is in Prism, but I had to rewrite the different kernel to be able to reach any kind of realistic performance. Otherwise, I would have been just catastrophic on FPGA. So that's, even if HLS takes C++, that's not a magic tool to transform CPU implementation into a FPGA. Only the graph can be reused directly. The kernel itself need to be changed.
So when people are selling Dataflow as a very fast way to map to different devices, at the end, it's not really true, right?
It's the idea is that you are able to map fast to different target, but the Dataflow doesn't address the implementation of the kernels. So if you want to have a kernel which is efficient, you need to write the kernel for your target. Even on if you have a small microcontroller compared to a large out-of-order processor, you're going to have something different. Even a GPU is going to be even different. So yeah, Dataflow definitely doesn't address that. We would need to have something which is even higher level. Nowadays, mostly domain-specific languages, which are sometimes able to address multiple platforms with limitation. Dataflow is one of them.
And are you adding some directive by hand in the kernel code?
Oh, the kernel code are 50% pragmas. I mean, but the kernel code would be they're implemented as kernel by themselves, but I have no knowledge of the global applications that I want to write. Then I'm adding all the pragmas to connect things together with the tool, with Prism.
Okay.
But the kernel itself, for example, if you have a loop, you want to execute this loop to have 2 iterations which execute in parallel, you're going to have a pragma. If you want to have a scratchpad which store your line to be able to compute a wall line, even if you read pixel per pixel, you're going to write an array explicitly in the kernel, etc.
Okay. So how do you compare? Because at the end, it looks like you are selling a very high-level way of, or at least higher level way of writing for programming for FPGA, higher than classical VHDL and Verilog. But when we go deeper in detail, we notice that it's not so high level, right? Because you have to write a lot of directive and so on, and you need to rewrite all the actors. So how do you compare your approach against something like high-level RTL implementation like Chisel?
That wouldn't be a comparison much for me, as we don't provide the real difference, I would say, for that compared to its HLS in general. Even if you're using Chisel, you need to think at the HL level, so you need to think cycle by cycle. So if you have, for example, a convolution here, those are image processing, but that would be the same kind of convolution same principle of convolution that you use in neural network that are implemented here. You need to store to have your wall box, for example. Here it's a 2D convolution, so 3 by 3. You need to store all those tokens, and you need to do a multiplication. So if you wanted to do that in RTL, you need to schedule all the storing of all the different data, the reading at the exact cycle, then your multiplication and addition, which are going to be pipelined to reach high performance, maybe 10 or 20 cycle. And you need to do all this scheduling by hand. So reaching this kind of performance can be done by somebody who writes RTL, but it's going to take them 3 months. For me, it's 5 lines of C++ and launching the HLS tool. And what this work adds to HLS, which I think is a big step forward, here is more an incremental progress, is that we, instead of representing a graph as a sequence of line in C++, which I think is limitative, we are representing that using our Dataflow tool. Well, that can be, I think it's nicer to use, but that's more nice to have. But the main challenge is buffer size, where those are going to depend on the implementation technology. So same kernel or different FPGA is going to have different performance, so different needs in terms of buffer, and those are very, very hard to estimate. I've seen even Xenix implementation where those buffer size were incorrect and not reaching highest performance. And here I think there is a big work to be done, and that's what we addressed in the automatic scheduling and buffer sizing.
Okay, but what kind of information do you need to give to Vitis for the? I mean, what kind of directive are you using inside the kernel?
Oh, inside the kernel, well, that would be for our tools. That would be any kernel that we can use. But right now, we most of the time providing forcing to have a pipeline implementation, forcing the number of memory access to be in parallel, and maybe the number of ways that it runs in parallel. But any C++ kernel, even a C++ HLS kernel which is badly implemented, could be used in Prism. We try to make to have applications which are realistic, so which are correctly implemented. But any kernel could be implemented as long as it reads and writes from FIFOs. And then Vitis is going to give us the timings.
Yes, the only thing is that the performance would be horrible, but it would work.
Yeah, it works. The performance will be horrible. Maybe we'll use more buffer, but that wouldn't be. Prism will do the best that it can with those kernels.
Yeah, okay. I see. And one last question. So you are not sharing any FIFO, right?
No, right now we have no resource sharing, either FIFO or kernels. That would be, I think, a challenge for us, given the type of abstraction of scheduling that we use, where we would have a hard time to say that resources are not used at the same time to be shared.
And is there a limitation of the size? I mean, of the application? Did you reach some limitation in that point? Because at some point, if you have higher, bigger application, you usually have a lot of FIFO, and then it's using a lot of memory of your FPGA in engine. Yeah,
right now, for example, this application, as it's implemented right now, if I target the Z board, it has, I think, 280 VRAM. So using this implementation right now, it doesn't fit in this platform. But it's already processing HD image. I don't remember the exact throughput, but that would be. I'll have to look at the throughput, but it's processing HD image at high throughput, so that would make sense maybe to get a bigger FPGA to do that kind of processing. But also we see the limitation here where we could gain a factor of 2 and be able to fit into this platform.
Yeah. Nice, thank you. Anyone have a last question? No? Okay, so let's thanks Mickaël for the presentation. And I'm going to stop recording.